Hello, everybody. Hello. About to begin section 3.3, properties of determinants. But I have to say one thing. I'm very sad to have to say this, but I learned that Zoom takes up a lot of bandwidth, and I learned that having the picture of me takes up some more. I don't know if it's a lot more, but it's whatever it is. So I'm gonna have to I'm gonna have to turn my camera off on myself. I feel bad to do that. I like to give you that personal touch, and I certainly don't want to deprive you of this beauty. But what can I do? It's really the quality of the math videos, which is what's important. So I have to preserve that. So I'm gonna disappear, and you're not going to see me very much. Okay, 3.3, properties of determinants. So we're going to learn all the things, what happens when you take the determinant of a product, the determinant of an inverse, the determinant of a transpose, so on and so forth. That's all the cool stuff that we're going to be doing in this section. So no further ado, let's look at what happens when you take the product of a matrix product and a scalar product. So this is a huge theorem. Let's just try this. Here's a matrix A, and here's a matrix B. Now I want you to pause the video, and I want you to do, well, don't pause yet. I want you to find, after you pause the video, I'm going to want you to find the determinant of matrix A. I'm going to want you to find the determinant of matrix B. Then I'm going to want you to multiply matrix A times matrix B with matrix multiplication and find the determinant of that product. So you have a bunch of stuff you got to do. Pause the video. Okay, we're back from our pausing. Let's move on. So here's our solution. The determinant of A, if you did it correctly, you should have gotten -7. The determinant of B, if you did that correct, you should have gotten +11. Now, as far as AB is concerned, the product AB is this guy right here, 8, 4, 1, 6, -1, -10, so on and so forth. And the determinant of the product, drum roll please, is -77. Now, did anybody notice, am I the only one here who noticed that -7 times +11 equals -77? In other words, the product of the determinants wound up being the same as the determinant of the products. Was that a coincidence, or does that always work that way? Well, guess what? It was not a coincidence. It always works that way, and we're going to prove it. So here's our theorem, theorem 3.5, that if A and B are square matrices of order n, obviously of the same order n, then the determinant of AB is equal to the determinant of A times the determinant of B. In other words, the determinant of the product is equal to the product of the determinants. So before we prove this, we have to do a little background first. Kind of background, I think it's a good way of saying it. Meaning to say that so forget the proof, forget the theorem. We just want to talk about elementary matrices. Now, in an elementary matrix, we know based on, now we know from theorem 3.3, well, I'll just show you 3.3 just to refresh your memory. Here's theorem 3.3, that when A and B are square matrices, and when B is obtained by interchanging two rows, then it makes a determinant negative. If I add a multiple of a row to another row, it does nothing to the determinant. And if I multiply a row by a constant C, then the new determinant is going to be C times the original determinant. And that is the fact. That's 3.3. We don't need that anymore. Bye. Now, back to here we go. So so we see from this now that we see here now that if I take an elementary matrix, meaning I take that, solve the identity matrix, and I switch two rows, then the determinant of that is going to be -1. That's just do it. You'll see. If you obtain, besides plus we know from the theorem, if you start with the identity matrix and you obtain my matrix E by multiplying one row by a non-zero constant, then the determinant of E is going to be C. And that also is very simple because you basically take the identity, it's basically the identity matrix, which is a whole just string of zeros, a whole string of ones down the main diagonal, and one of those ones is being turned into a C. So yeah, it's very simple, very obvious for a million reasons. And if you obtain E by adding a multiple of one row to another row, then the determinant of E is just one. So basically, the determinant of E is either going to be -1, +1, or it's going to be the constant that you multiplied by. Now, additionally, by Theorem 212, now what is Theorem 212, you ask? Theorem 212 is right here. Theorem 212 told us that if A is an n by n matrix, then the following are equivalent. And number 5 is that it can be written as the product of elementary matrices. Now, so plus, okay, I just have to say, I had to make a little correction. I pulled up the wrong theorem. Theorem 212 is this one right here, that if E is an elementary matrix, which is obtained by performing an elementary row operation, then the same elementary row operation is performed on an n by n matrix, then the resulting matrix is given by the product EA. In other words, when I multiply, which is basically saying that well, let's see what it's saying. So going back to right here, so if E results from performing an elementary row operation on I, the same elementary row operation performed on B, so therefore, the matrix E, therefore, the determinant of EB is equal to the determinant of E times the determinant of B. Well, why is that? Because so the reason this works is because the product EB, as we said, it either switches a row or it multiplies a row by a constant, or it adds a multiple row to another row, and that's either gonna, like we said before, that's either gonna keep the determinant the same. It's gonna multiply the determinant by -1. It'll multiply the determinant by that constant. This is just basically a fancy way of saying what we've been saying in plain language already. Now that we know this, we've just a little bit left, and then we're going to actually start the proof. This is really still kind of pre-proof. So here we go. So first of all, before I do that, there's one last step I got to do. I want to generalize this. Let's say you have a whole bunch of elementary matrices times B. Well, E1B does whatever it does, switches rows or something. E2 now takes that and multiplies one of the rows by a constant. E3 takes that and adds a row to another row, and so on and so forth. Well, it's a succession of operations, so I could just break this up, that the determinant of this whole big giant product is B times the determinant of V1, which again is 1, -1, or C, times the determinant of V2, dot, 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 all the way up to EK. Now we're finally able to start the proof. So there are two cases we have to consider. One is that if that's not, I highlighted it, good. One is that if case 1 is when A is a non-singular, and case 2 is when A is singular. So we're going to do case one first. If A is non-singular, now non-singular means it has an inverse. If A is non-singular, then by theorem 2.14, A can be written as the product of a bunch of elementary matrices. And the determinant of AB is going to be the determinant of these elementary matrices times B. I'm sorry, times B, because A is all these E's. A really consists of all these E's. So AB is all these E's times B. Well, the determinant of this massive thing now, which is, we're taking the determinant of the whole thing, the determinant of this whole massive thing here is all these separate little determinants. And we know that these separate little determinants, now here's what I'm doing, it's very slick. I separated all the determinants, but then I'm going to recombine them. I separate them and I'm going to immediately recombine them, except I'm not going to I'm going to leave the B out. So I'm recombining all the E's, but keeping the B separate. What is all the E's? All the E's, that's just matrix A. So look what we have here. we started with the determinant of the product AB, and we wound up with the determinant of A times determinant of B. And there was a product of the determinants. So if A is an invertible matrix, a non-singular, which means invertible, then I can do this. Now, that's case one. Case two, suppose A is a singular matrix. It actually is not invertible. Well, we learned that if it's a singular matrix, then it is row equivalent to a matrix with an entire row of zeros. And which now I don't need any fancy theorems to tell me that if I have an entire row of zeros, then the determinant of A is zero. And why? Because you just when you take the determinant, you just go down that row. So it doesn't matter what everything else is because you're multiplying everything by zero. That's basically what we get from theorem 3.4. And not only that, but because A is singular, meaning no inverse, so that means that AB is also going to be singular. I mean, if I take a singular matrix and I multiply it by any other matrix, I don't care what the other matrix is, it's going to stay singular. Singularity you can't just get rid of singularity by multiplying it. And now it says here, if AB were non-singular, then A times B, AB inverse equals I would imply that A is non-singular. Let's just do, this one little step, let's just look at that in slow motion. So if AB was invertible, there'd be an AB inverse. And A times AB inverse, of course, would be the identity matrix. But matrix multiplication is associative, so I could drop these parentheses here. I could drop these. I don't have to deal with dropping these parentheses, and it's more complicated, with the. Anyway, I digress. I could drop the first set of parentheses, so I have A, B, but now I can put in a new set of parentheses. I can put parentheses here, and then put one over here, and we have A times this whole big mess here is equal to I. Well, that means this whole big mess here, which I'm going to highlight, this whole big mess that's inside the bracket is by definition A inverse, because I took A, I multiplied by this big mess, and I got the identity matrix. So that means this is the A inverse. But we just said that, but our premise is that A is not invertible. We're dealing in the case where A is not invertible. So that's really what this is trying to say. Anyway, that's what that one little step was explaining. Well, if AB is not invertible, if AB doesn't have an inverse, then that means the determinant of AB is equal to zero. So it's true that the determinant of AB is equal to the determinant of A times the determinant of B, because basically it's just saying zero equals zero, of which, and even I know that zero equals zero. Okay, now we're going to move on to another theorem. Now this theorem is actually very simple. If I take a matrix and I multiply the entire matrix by a constant, the determinant of that product, so this is a product of a scalar and a matrix, it's not going to be C times the determinant of A, it's going to be C to the nth power. Why is that? Very simple. Because if I multiply a matrix by a constant, I'm multiplying each row by that same constant. So we know when I multiply the first row by that constant, it multiplies the determinant by C. But I'm also multiplying the second row by that constant, which multiplies the determinant by another C. And then the third row, which then contributes another C. So finally, the nth row, I get C to the nth power, and that's why it says C to the nth power. So you got to be very, very. Sometimes students get confused about this. They know that when you multiply one row by a constant, then the determinant is multiplied by that one constant. But here, when you multiply a determinant, when you multiply the entire matrix by a constant, it means you're multiplying all the rows. So you're doing the same process n times. Okay, well, let's move on to onward and upward striving. The book points out, in other words, we're learning here about the product. We learned that the determinant of the product is equal to the product of the determinants. Well, you can't do that with sums. You can't say that the sum of the determinants is equal to the determinant of the sum. It just ain't going to work. Sorry, chump. And they give a simple counter example here. It's that you see it just don't work. It reminds me a little bit when students think like the square root of a plus the square root of b is equal to the square root of a plus b or something like that, which it just don't work. I mean, and I don't have to start proving that it doesn't work. We never even established it. So, anyway, so there you go. Now we're going to get to inverse. So we're going to look at determinants and the inverse of a matrix. And so we just finished seeing how determinants, products and determinants, mix determinants of products. Now we're going to look at determinants of inverses and inverses and all the interplay between determinants and inverses. So first of all, when you just look at a matrix, here's matrix A and matrix B. I'm just looking at them. Here's matrix A, here's matrix B. And can you tell if these matrices have inverses or not? Oh, it's hard. I mean, you could work it out. You could go through the whole process and see, see if it works, see if the Gauss-Jordan elimination, see if you wind up getting an inverse from that. Well, can you tell that just by looking at it? Well, it's very hard to tell just by looking at it. But the next incredible theorem, actually helps us with that. And that is that the determinant that if a square matrix is invertible, if and only if the determinant does not equal 0, which means that if the determinant does equal 0, the matrix is not invertible. Well, let's just look at matrix A. Notice that the second column is exactly -2 times the first column. So if I would take the third column, sorry. So if I would multiply the third column by 2, add that on to the middle column, I'm just going to get a whole slew of zeros down the middle. And we know that when you have a whole column full of zeros, the determinant is going to be 0. So I just figured, just by looking at this and just doing one mental step, I was able to see that A will have a 0 determinant, hence A will not be invertible. B, on the other hand, I would actually have to figure it out, because I don't see a very quick, simple way to eliminate a whole row or column. Anyway, let's first let's figure out this theorem. Now, this theorem is very cool and awesome, and the proof is going to be really very simple based on what we just did. Once we know about products, because if A is invertible, that means it has an inverse, and if I multiply A times the inverse, I get the identity matrix. That means that we learned that the determinant of a product is equal to the product of the determinants. So that means the determinant of A times the determinant of A inverse equals the determinant of the identity matrix, but that's equal to 1. Now we know if I have two numbers, so the determinant, as you know, is just a number. Determinant. So if I have one number times another number, I'm multiplying two numbers, and my result is 1, then it's impossible for either one of these numbers to equal 0. It's kind of like it reminds me a little bit of what we do when we factor like polynomials. When you factor polynomials and set each factor equal to 0. See, but hear what I'm saying, because there you have a product that equals 0. If you have a product that equals 0, at least one of the numbers has to be 0. But here, I have a product which is not equal to 0, so none of the numbers could be 0, because if any of the numbers are 0, the product would have to be 0, not 1. And so that's now this is an if and only if proof, so I got to prove it in both directions. So I've shown that if A is invertible, then the determinant will not equal 0. Now, as far as the other direction, that we can kind of do more just with thinking in words. So for the other direction, and this paragraph is really going to say it all, but we're going to assume that A has a non-zero determinant, right? And then we're going to use Gauss-Jordan elimination until we reduce it down to a reduced row echelon form, which is row equivalent to A. That's going to be our new resulting matrix we call B, B for Barry. And now because B is a reduced row echelon form, it's an n by n matrix and it's row echelon. So either B is going to be the identity matrix, or B is going to have at least one row, which is all zeros. But wait a second, if B has a row that's all zeros, that means the determinant of B is equal to 0, which would imply that the determinant of A is equal to 0, because that's what you do. The determinant of A is just determinant of all those elementary matrices times B. Those are all non-zero. So, but wait a second, we're dealing on the side that the determinant of A is non-zero. So that's what we're saying. The determinant of A is non-zero. So we can't have a determinant being 0. So therefore, the only possibility is that when we reduce row echelon it, and we get that matrix B, that has to be the identity matrix. In other words, A is row equivalent to the identity matrix, and by theorem 2.15, you know that A is invertible. And what is theorem 2.15, you ask? That is this one right here. If A is an M by N matrix, A is an M by N matrix, and number 1 says A is invertible. Number 4 says A is row equivalent to identity matrix, and these are all if and only if things. So if A is row equivalent to the identity matrix, then A is invertible. We see that from theorem 2.15. Okay, moving on. Pow. So we're done. A is invertible. So we've shown that if A has a non-zero determinant, A is invertible. So here we have, again, a beautiful thing saying that a matrix is invertible if and only if the determinant does not equal 0. And you know what? Now we can add this to the list. We can actually make 2.15 even better. Oh, we'll do that later. Now, so which of these matrices has an inverse? Well, this one here, which we saw this one before, has a 0 determinant. So therefore, it is invertible. And matrix B, which has a non-zero determinant, is invertible. We looked at these earlier before. And now, what about the determinant of an inverse matrix? What about the determinant of an inverse matrix? Well, the determinant of an inverse matrix is going to be the reciprocal of the original matrix, and that's really simple. That really just follows from that product rule that we said. Because if A is invertible, so A times A inverse is equal to the identity matrix, and that means that the product of the determinants is the same as the product of a determinant of the product, which, and the product of course is I, so that it equals 1. So if the determinant of A times the determinant of A inverse equals 1, that means they're reciprocals. So A inverse is the reciprocal of A, and that's kind of cool. Which means that if I would say find the determinant of the inverse of a matrix, I give you a matrix here, and I say here's matrix A, find the determinant for matrix A. Well, I'm sorry, here's matrix A, find the determinant for A inverse. Well, before this, I would have to go through all the trouble of finding A inverse, which could be pain, and then take the determinant, which is another pain. But now, all I got to do is take look at A, take the determinant of A, reciprocate it, flip it upside down, and I got my answer. That's exactly what we're going to do. Okay, so I want everyone to do that. I'll give you pause the video and everyone do that. Okay, video is unpaused, and now here we go. And the determinant, you should have gotten 4 as the determinant of the original A, and which means that the determinant of the inverse is 1/4. And now I'm going to make my list even bigger. We had 2.15. We're going to put it on steroids. It's just an expression. Because we had all these equivalent conditions. We had 5 equivalent conditions. Now we can add condition number 6. So A is invertible. AX equals B has a unique solution. AX equals 0 has only the trivial solution. A is row equivalent to identity. A can be written as a product of element matrices. And now condition number 6, the determinant of A does not equal 0. So all 6 of these things are equivalent, which means if I know any one of these 6 things, I know all of these 6 things. And that's which is very nice, because if I want to prove something has only a trivial solution, I could prove that the determinant is non-zero or whatever. I have all those options of showing things, but they're all equivalent. Now let's look at systems of linear equations, because that's obviously a big topic in linear algebra, and we're going to use this. But I want to look at number. What do I want to look at? I want to look at number 2 and number 1, and number 6. So number 1 is A is invertible. Number 2 is that AX equals B has unique solution, and number 6 is that the determinant is non-zero. So if I want to look at a system of equations, now unique solution. When you do a system of equations, it's always fun when you get an answer, as opposed to getting no solution or infinite solutions. It's always awesome if you just get one answer, which is what condition 2 is saying. Unique solution means you just get one answer. Well, so will you or won't you get that one answer? Well, what I could do is look just at the coefficient matrices. I actually showed you more than one to show, so I can't take it back. I could just look at the coefficient matrices, find the determinant. So here, when I take the determinant of these coefficient numbers, I notice I had to fill in a 0 over there. I get a 0 determinant. In fact, these are numbers we've seen already. When I take the determinant of these coefficient numbers, I get -12, which is not 0, which tells me that that problem B, there will be a unique solution. What that is, I don't really care about that right now, but there will be a unique solution. And problem A will not be a unique solution, which means either there's going to be no solution or it's going to be infinite solutions, but you're not going to have that cool, awesome situation like we had before. And so that, my friends, is the story. Now let's move on to transpose. So again, just wrapping up. So this chapter, this section really is three things. One is determinants of products. The other one is determinants of inverses, and finally determinants of transposes. And it should come as no surprise to anyone that transposing does not affect the determinant at all. And we'll see an example of that, which means that if A is a square matrix, the determinant of A and the determinant of the transpose of A are exactly the same thing, which makes sense, because don't forget, a transpose is when you sort of flip the matrix around, the diagonal. And well, let's just, for example, so let's look at matrix A. So here's matrix A. Well, let's say we take the we expand this on the second row to get the determinant, which is a great choice because you have a couple of zeros on the second row, and you do this, and here's what you get. I'm gonna go make the. Well, let me just go through this. I'm gonna go through this actually smaller, so I can fit it all on one page. And yeah, it's like even smaller. I want to fit it. Okay, so the determinant of A is going to be this stuff right here. Now for A transpose, instead of going on the second row, I'm going to go on the second column. You see, makes a lot of sense because the second row of the original is the same thing as the second column of the transpose. And when I do that, I want to get in like the exact same numbers. I get everything's going to be exactly the same. Not only is the final result the same, but the numbers themselves are all the same. So that's it. And that's really why the determinant of a transpose is equal to the determinant of the original matrix. I want to give a little homage here now to an old friend of ours, Laplace. If you ever took differential equations, you've seen Laplace transforms. I know if you took differential equations, this surely brings back pleasant memories. Laplace is very important to differential equations. Laplace is also very important to linear algebra because he's the one who really proved that you can take a determinant by going down any row or any column, and that's a huge thing. It's a huge thing. Anyway, so yay for Laplace. Anyways, this concludes section 3.3. It's been loads of fun. We must do this again sometime, and we'll see you all next time.